In this video, we're going to talk about complex ions. But first, what is a complex ion? A complex ion is the combination of a transition metal cation with a ligand molecule or a ligand ion. So let's use an example. Here we have the silver metal cation. It has a charge of +1. And we're going to react it with two ligand molecules, in this case, two ammonia molecules. In this case, the ligand is not an ion, it's a neutral molecule. And it's going to form this particular complex ion. The diamine silver cation. Now, what is the coordination number of that complex ion? The coordination number is 2 because it's attached to two ligand molecules. So this is the ion, or the metal ion. This is the ligand. And here we have the complex ion. Now, for complex ions that have a coordination number of 2, the geometry will be linear, as you can see from this particular drawing. And so that's a basic introduction into complex ions. So now let's look at another example. The hexacyanoferrate ion. Identify the ligand and also determine the coordination number and the oxidation state of Fe. The ligand in this example, it's not a molecule, but it's a polyatomic ion. In this case, it's cyanide, which has a Lewis structure that looks like this. The carbon bears the negative charge, or the negative formal charge. Now, the coordination number is basically the number of ligand ions attached to the transition metal cation. So the coordination number in this example is 6. Now, how can we determine the oxidation state of Fe? Would you say it's +3, -3, +4, -2? What is it? Well, let's write a reaction. So we know that Fe probably has some charge, which we'll call X. And it's going to react with 6 cyanide ions to produce the hexacyanoferrate ion. Almost lost the word there. So let's write an equation where the total charge will remain balanced. So Fe has a charge of X. Cyanide has a charge of -1, but there's 6 of them. And the product ion, or the complex ion, has a net charge of -3. So X minus 6 is equal to -3. So if we add 6 to both sides, we can see that X is -3 plus 6, or +3. So this is the oxidation state of Fe. So Fe has a +3 charge. Now, there was a guy called Alfred Werner, and he came up with a theory for coordination compounds and transition metal ions. And he basically stated that transition metal ions have two types of valence, and that is that the way that these metal cations can combine with other things like ligands and ions. And the two types of valence that these metal ions can have is called, the first one is the primary valence, and the second one is the secondary valence. Perhaps you've heard of these terms. And in the case of the Fe3+ ion, as it relates to this particular complex ion, what do you think the primary valence and the secondary valence of this transition metal cation is? The primary valence has to do with its oxidation state, and thus the way it forms ionic bonds. The secondary valence has to do with the coordination number, and so it relates to how it interacts with ligands, and those ligands could be ions or molecules. So in this case, The primary valence is positive 3 because that's the oxidation state of Fe, and the secondary valence is 6 because the coordination number is 6. It could be attached to 6 ligands. Now, what type of geometry does the FeCN6 3- ion have? If the coordination number is 6, the geometry will be octahedral. And so it's going to look like this. And so that's how you can draw this particular complex ion. And if you want to show the octahedral structure, you can make it look like this. So that's the octahedral structure of this particular complex ion. Now, if the coordination number is 4, then there's two types of geometries that can occur. One example is the tetrahedral geometry. Another one is the square planar geometry. So the tetrahedral geometry looks something like this. Or it can have a square planar geometry, which looks like this. So if you have a coordination number 4, the geometry could be any one of those two. So keep that in mind. Now let's talk about the coordination numbers for certain transition metal ions. Now let's say if we have a transition metal ion with a charge of +1, such as copper plus or Ag plus. The coordination number of copper +1 is 2 and 4. For silver, it's only 2. And so if the charge is low, the coordination number is relatively low. But notice what happens if we increase the charge, let's say to +2. So cobalt, for example, the cobalt 2+ ion can have a coordination number of 4 or 6. Nickel 2+ is the same. Fe2+ can be up to 6, and zinc 2+ can be 4 or 6. Now let's look at the +3 ion. One example is gold 3+, which has a coordination number of 4. Chromium 3+ has a coordination number of 6, and cobalt 3+ has a coordination number of 6. So notice the general trend. As the charge on the transition metal ion increases, the coordination number generally increases. And it makes sense, because if a metal ion has a very high charge, it makes sense that it can bind to more ligands. Now you need to be familiar with the different types of ligands. The first type is called a unidentate, also known as a monodentate ligand. So uni and mono is associated with the number 1. So this tells us that the ligand can only make one interaction with a metal ion. Some good examples of these types of ligands are water, ammonia, chloride, cyanide, thiocyanate, just to name a few. So in the case of ammonia, it has one lone pair, and so it can only form one interaction per molecule with a transition metal ion. A bidentate ligand can have 2 interactions per molecule. Bi is associated with the number 2. So one example is the oxalate ion. It has 2 oxygen atoms with a negative charge. And let's use a zinc metal cation. So this is one interaction, and that's another. So there's 2 interactions per molecule, which makes it a bidentate ligand. Another example is ethylene diamine, which you can abbreviate it as EN. So this particular ligand can also make two interactions. Each nitrogen atom has one lone pair, which can bind with a transition metal cation. So this is one interaction, and this is the second interaction. So that makes ethylene diamine a bidentate ligand. So those are known as chelating ligands. A chelating ligand can interact with a metal ion in more than one way. So bidentate ligands are chelating ligands. Now let's talk about coordination compounds. And here is an example. A coordination compound is neutral overall, but it consists of a complex ion and a counter ion. What do you think is the complex ion in this example? Well, you can clearly see it. It's in brackets in this particular example, and so it's CrNH3 6. Now, what do you think the charge or the oxidation state of chromium is in this example? Now, we know that cyanide has to be the counter ion. It's there to balance the charge on chromium, and there's 3 of them, which indicates that chromium has to have a +3 charge. So this particular complex ion has a +3 charge. So this is the complex ion, and in this example, this is known as the counter ion. The counter ion that we have in this example is negatively charged, so it's called an anion. But it doesn't always have to be an anion. It can be a cation. In this example, the complex ion is the cation, and so the counter ion has to be an anion. But sometimes the roles can be reversed, like in this example, K3FeCN6. So this is the cation, and this has to be the anion. So this time the anion is the complex ion FeCN6 with a -3 charge. And the cation is the counter ion, which is used to neutralize the -3 charge of the complex ion. And so we have 3 of them. And so the coordination compound is always neutral. The net charge has to be 0. So that's it for this video. Hopefully it gave you a basic introduction into complex ions, ligands, and coordination compounds. Thanks for watching.